Hello friends, welcome to a new video. Today we'll be discussing the most favorite question, that is the high level system design of long URL shortener. So what is the need of tiny URL in today's world? It allows users to shorten the long complex web address into concise, easily shareable links, making it extremely useful for platforms like social media posts or text messages, um, and even the communication messages that we receive for bill payments and so on. A shorter link is more visually appealing and easier to remember. It provides analytics to track how many times a link has been clicked, which can be valuable for marketing. So all in all, it's a convenient way of representing a long URL which contains so many characters, and it becomes easy to manage the long URL in form of a tiny URL. So what are the functional requirements that we need to consider while designing high level system design for a tiny URL? So first is we'll be given a long URL, and the application service should generate a shorter and a unique alias for it. So whenever the user hits the short link, the service should redirect back to the original link. That is the bigger one. So the other thing that we need to consider is the expiry time, and we can't store the URL forever, the short URL. So we need to have the expiration time as well. And as far as non-functional requirements are concerned, we need to ensure that the system is highly available, scalable, because there could be several reads and writes happening in the range of 30 million plus, and there should not be a single point of failure. So these are the non-functional requirements and functional requirements. Let us see how we are going to fulfill those as we discuss the system design. So first we need to calculate the data capacity for, let's say, 5 years. So the long URL, which may contain up to 2048 characters, so approximately 2 KB. Short URL, 17 characters, so 17 bytes, and then what time the short URL was created and what time it is expected to be expired. So we can approximate the total space that we'll be needing to store data for a single long URL will be close to 2 KB, and let's assume that there are 20 million users who use this tiny URL service. So for a month, considering 2 KB space for one single long URL, so we may need 40 GB of data we need to manage for 1 month, and then for a year we need to manage 0.5 half terabyte of data. And so now we have a clue for over the period of next 5 years we need to manage close to 2.5 terabytes of data. So let us discuss the various techniques that can be used to generate the tiny URL. So for the first technique we can use base 62, and before that let us understand why base 10 is not sufficient enough for our requirement. So it contains numbers 0 to 9, so it will give us or provide us only 10 million URLs, which are insufficient because our users itself we have assumed as 20 million. So at least we need to provide generate URLs which are 10 times more than our users, or even more than that. So for base 62 it contains the upper and lower case of alphabets A to Z as well as 0 to 9. So in that way it can help us generate tiny URL of 7 characters, which is close to 3500 billion URLs. So this capacity is more than enough for next 100 years for us to maintain the tiny URLs. Now before understanding how the base 62 algorithm works and how it writes the tiny URL into a DB, let us understand which type of DB is more suitable for our application. So mainly there are two types. One is the NoSQL, another is the relational database. So in relational database, the schema will be fixed. The tables will have rows and columns, whereas uh, in the NoSQL, it will be flexible and it will be schemaless. It will be based on key value relationship, and we call it as document. Then for scalability perspective, the relational databases can scale only in vertical order, and horizontal scaling is quite challenging. So we use data sharding over here, and as the scaling requirement increases, it becomes more and more complex and tedious task to manage data using data sharding. Whereas for NoSQL, it can scale horizontally, so it is uh, far more easier to manage the growing data. Uh, this is ACID compliant, whereas this is offers eventual consistency. So although the relational databases have strong consistency, and NoSQL will offer the eventual consistency, that is, it replicates the data across all or creates a copy across multiple DBs, so there may be a lag. So that's why we call it as eventual consistency. And yeah, these are the differences, and we will be tempted to go with NoSQL databases for scalable applications. So let us take a look how base62 works and stores the tiny URL into the DB, and then whether it's a reliable solution or not. So first let us focus on the client one who is trying to generate a tiny URL for his long URL A. So once he raises a request, and then the load balancer will direct it to server 1, and the server 1 will in turn using a random decimal, say 1000 or say 10,000, it will try to generate a 7-character tiny URL, which will then be since it's not present in the DB, it will be written and stored. Now what if the client 2 is also trying to store the tiny URL for its long URL? So both of them approach at the same time to the load balancer, and they will be pointed to server 1 and server 2 respectively, and then they will approach the base 62 algorithm, whose input they can end up providing the same decimal number, say 1 million, and they will again get the tiny URL will be the same. So since it will be the same and DB is not yet having any values associated with this particular tiny URL, so both of them get stored. Now whenever we try to retrieve next time for, let's say, long URL B, and long URL A was stored the last, so it will retrieve this tiny URL. Or in other case, if let's say someone is trying to retrieve the long URL A's tiny URL, and for some reason B was inserted later, so it will return the tiny URL of B. So that leads to collision, and we need to avoid this. So we need to have a better design to use base 62. So let us take a look at one more technique, that is the MD5 hashing algorithm, which could also be considered for generating tiny URLs. So it contains it encodes the long URL using the MD5 approach, and takes only the first 7 characters to generate tiny URL. So it the long URL is fed into the algorithm, which produces a 128-bit hash value, and then again we'll truncate it so that we can obtain some short URL. And again we will be let's say in these 28 numbers, we'll be interested in the first 7 string values, or the first 7 characters of this truncated URL. So uh, there's a advantage of using MD5 hash algorithm is it will always generate different 128-bit hash values, the probability of having the same hash value is very low. But there is a challenge with MD5 algorithm is that whenever we try to use the first 7 characters, this may be the same with the other hash value that was generated for some other long URL. So again, we cannot, uh, if it's a NoSQL database, then there is no way to check using the if-else statement that whether the given tiny URL exists in DB or not. And anyways, we cannot use the relational database because of the scaling issue. It's very hard to scale out. So the only option is NoSQL, and NoSQL cannot use the if-else statements. So we may end up again giving a new string and generating a new hash value, and that will lead to lot of time delay. So in such case, we can always use the third technique which works the best, and that is by using a counter. So it's a good decision for scalable solution because counter always gets incremented, so we can get a new value for every new request. So here we are ensuring that uh, every time one of the apps servers try to generate a tiny URL, the counter value will increase, that is the decimal values will increase, and will always be guaranteed that will always generate a unique tiny URL. But however, here also there is a challenge. Let's say there is a single counter which ranges from 1 million to 2 million values. So if server 1 and server 2 both are dependent on counter 1, so let's say the counter 1 goes down, then in that case we need to have a counter 2, and counter 2 doesn't knows that at which value, let's say 1 million or 1,000,010 was assigned, and from which value it needs to restart and assigning the new decimals or the new tiny URL values to server 1 and server 2. So that leads to a single point of failure. So the best possible solution can be using a distributed system, that is a zookeeper, which acts as a controller of multiple counters, and every time a app server approaches zookeeper, it will always maintain a unique ID for each app server and always assign unique counter to them. So in this case, in the given diagram, for the first server, it will assign the counter values as 1 lakh to 2 lakh. Then for N2 it will assign 2 lakh to 3 lakh, and for N3 it will assign 3 lakh to 4 lakh. So whenever these app servers try to generate tiny URL using these decimal values, it will be guaranteed that they will always get a unique tiny URL. So this design will ensure that there is a guaranteed no collision system. Now what if node 3 goes down and node 4 comes up, and now node 4 needs to have completely new set of decimals. So because of the presence of zookeeper, what it will do is it is aware that although the node 3 has gone down, and so it will block these values or these counter, and it will assign the new counter 4 lakh to 5 lakh to N4. So as a result, the system is very resilient for any kind of failures, and also there is no single point of failure over here. And also we are using the cache, so whenever there is a read request, the user doesn't needs to always read it from the DB directly. As long as the timeout doesn't occurs, he can fetch his tiny URL directly from cache. So that is one of the advantages, and we'll have a separate video on Redis cache soon. So most of the functional requirements and the non-functional requirements have been taken care using this system design. I hope you have understood and enjoyed the design of tiny URL system. Thank you so much.